Now I'll go back and get the screen sharing done again. And what I just had up here is no longer available. I don't know why it does this kind of crazy stuff. 8.4. Okay. And now let's go back to screen sharing. There, now we can do 8.4. There's just too many moving parts here. Okay. So let's go from current slide. And it looks like maybe, wait, that's not what I wanted to do. Looks like maybe, yes, Ashton's back, I think. All right. So let's go back to current slide. One of these days it'll all get loaded. I don't know why it's being so obstinate today. Probably because I'm in a hurry. Okay. But, alright. There we go. Finally, it showed up. So Ashton, I hope you weren't waiting long. I've been trying to get things lined up. At first it said I didn't have any internet when I had 4 bars, and then it's just been kind of nuts. Okay, so I think we're ready to go now. Glad all of you are here, 100% attendance. And I wanted to remind you, what is tomorrow? Yes, absolutely. Now, maybe not all of you can vote, but all who can. If you haven't already voted, my wife and I have, please vote. Don't forget it, you know, and we will just, you know, I can't speak for all the instructors, but I think I've said to all my classes that meet on Tuesday, Thursday, if you can't go any other time, go during my class. But if you can do any other time, vote and then get to class as soon as you can. But it's so important that you vote. So that said, I see a couple of chats or messages. Is there anything I need to see here? Okay. Okay. I appreciate you saying that, because this, let me see if I can get it up here now. Yeah. Let me see if I can get, okay, I'm going to have to, okay, I'm going to have to do some new manipulating here. So hang on, Sloopy, I'll get with you in just a minute. I didn't have Blackboard open at the moment, so let me get it open now. So this is going to take just a few minutes to do that, and then I'll come back to screen share. Okay. Okay. Close, but not quite there yet. Okay. Okay, there we are. Not quite there yet, but close to it. Let me get the new screen share open then. Oh, here's the announcement about our class today. Get the new share open. It just takes a while. Okay. You can see my Blackboard now. Math 126, this class. Yes, sir. Okay, good. Let me see if I can find where it is. Now, one of the problems is with all the other things up here, it's hard for me to be able to click on the icons that we need to do. Now, does anyone remember which week I put that out there? Was it week 9 or before that?
Week 9.
Was it? Okay, let me see. Yep, chapter 7 test. Let's see if it's here. Okay, here we go. All right, yeah, that is a Word file, and I was afraid of that. Let me just see if maybe I got to move some things around again so I can see where. Okay. Okay. Let me go back up to. Yuck. Okay. Okay. If you'll notice here, when I sent this email, I said attached is it's also located in week 9. This is a Word version of the test. If any parts of it are not readable on your computer, please let you know. And that's what you were just letting me know, right? And I'll send the PDF version of the same test. Let me see if I have that PDF version handy. So this is going to take, okay. Again, let me see. There's so many moving parts here. So there's computer, USB. Oh, I could have gone here. Sorry about that. Okay. There it is. I don't know if you can see all this or not. 126. Okay. I think this is test 2, right?
Yes, sir.
Okay. I have probably several versions of this test out here, so let me make sure I'm looking at the right one. Okay, is this how it began? Find the area of the region, yeah, chapter 7 test, bounded by the equations y is equal to 16 minus y squared, x equal y minus 4, integrating with respect to y. Is that the right one?
Yeah, I got the test printed out because I usually just print it out.
Right.
I scanned it.
Oh, no. But can you see my screen now? That's what I'm asking. Oh, okay. Let me. I've got. You see, when I've got this here, there we go. Things cover each other, things up. Okay. Here is the test. Is that the right test? Are these some of the places that you can't read?
Yes.
Okay.
I can already see the stuff that you was missing too.
Say again?
Yeah, I can see what was missing now.
Yeah, exactly. Okay. What I'll try to do is get this. I don't have it in a PDF format now, but I can do this evening probably. Sometime between 4 and 6, I'll try to do a PDF version of this and then post it out there. Both under, if I can put it under week 9, I'll put it there, but if not, I'll put it under messages, okay? But this is the type of things that you're not seeing, like number 2, y equal. Is that one that you can't see?
Yes,
Okay.
Y equals 1.
Yeah, you can't see that. And number 3, y is equal to 14 minus x squared over minus 14. Those are the type of things you can't read.
Yes, sir.
What it is, it's sorry Microsoft product. They come up with a new version and then don't let the older versions read it. So they make you buy a new product. And this computer is not my computer. It came from the campus, and they had a more updated version probably of Microsoft Word than you have, and therefore you can't do it. So I'll try to get this one done, like I said, this afternoon sometime. I don't have time to run down and do it today. I mean, right now. That would take too much class time, but I'll try to get it done this afternoon. Is that okay? Okay. No, it's Microsoft. It's not you. Sorry about that. But those are the, I mean, unless you just want to write them now, you can, but it'll be so much easier if I mean, I would think it would be easier for you to have it in front of you rather than having to write it in. Is that right? Okay. All right. Sorry about that. But that's why I put that message out there, and I'm glad you responded. If you can't read it, please let me know, and I'll send the PDF. Okay. So I'm going to see if I can get back to screen sharing. I'm on screen sharing now. But let's see, PowerPoint show. Is that the right one? Yes, I think it is. All right, any other questions, issues, concerns, problems? Okay, I'll try to get that done this afternoon sometime between 4 and 6, hopefully. I just got back into town and I'm already exhausted, but I'll try to get that done first thing as soon as my 3 classes are over today. All right, now where we left off before, we're in Chapter 8, Integration Techniques and Improper Integrals, mostly integration techniques now. We're in Section 8.4, Trigonometric Substitutions, as opposed to trigonometric integrals that we did before, okay? And we're here on the top of page 542, Example 1. Find this integral, okay? Now what you focus on here is this part right here, okay? Now, if this had been an x up here, just a u substitution will work. But no, you got an x squared in the radical, you have an x squared out of the radical, but it's in the denominator. So this is not conducive for any other type of substitution but a trig substitution. Now, which trig substitution do you use? Because this is 9 minus x squared, here's this trig substitution. Let me make sure I say this right. Believe it's u equal 3 times the sine of theta. Okay? No, I'm sorry, not u, x. That's the thing we're substituting. Okay, wait, I'm on the wrong screen. Okay, the brain's not here yet today. It may catch up some of these times. Okay, let's let x equal. All right. See, this is different from before. Before, you'd pick the part in here, most complicated part. I can't get my pen to show up. There it is. Okay. You would pick the most complicated part and let u be that. Not so when you're doing a trig substitution. We pick the x here that's in the most complicated part, and what would be the trig substitution that would go there. So let x equal 3 times the sine of theta. Now, before with the let u equal something, we just proceed with du and on like that. We're going to do that too, but we've got several things to do here. The first thing we've got to do is square the x, okay? So I'm going to go on this track here, then, this is a different then than we normally have, x squared is equal to 9 times the sine squared of theta. Follow that? Okay, if x is 3 sine theta, then x squared is 9 sine squared theta. You just do a square there. Okay, then the next thing we do is do 9 minus x squared. Well, 9 minus x squared is 9 minus 9 sine squared theta. Now I'm doing this in gory detail here. After a while you'll skip a bunch of these steps, right? Okay, Now for some reason there we go, my wires are getting all tangled here. There's just too many moving parts here. Okay, all we did was, what we're looking for is, if I could get the pen to show up. Where in the world is the pen now? There it is. Here we have 9 minus x squared. Here's 9 minus x squared, but x squared was 9 sine squared theta, so that's what we got. Well, let's put that in a radical, because that's where it is. It's inside the radical. 9 minus x squared is the square root of 9 minus x squared is the square root of 9 minus 9 sine squared theta. Well, what's that? Well, right here you can see you can factor out a 9, but that's still under radical, so it's square root of 9 times, factoring out a 9, you have 1 minus sine squared theta. Hey, we know what that is. Square root of 9 is 3, and 1 minus sine squared theta is cosine squared theta. And the square root of cosine squared theta is cosine theta. Now, was that too many skip steps, or do you follow that? All right. I hope that means you follow it. All right. Let's go back here to this side and then do your normal then here. Dx is equal to, if x is equal to 3 sine theta, dx would be 3 times the cosine of theta, d theta. Yay or nay? All right. So now I think we're ready to set up our new integral here. Okay? The dx here is, I'm going to put it all in the numerator right now, and then we'll figure what we're going to pull out. The dx is 3 times the cosine of theta d theta. That's from right here. Okay? Dx. The x squared we have here is 9 times the sine of sine squared of theta. Okay? And your square root of 9 minus x squared, that's what this is. That's your 3 times the cosine of theta. Okay? Now, let's see what we got. The 3's can go out here. The cosine thetas can go out here. Of course, cosine theta can't be 0. Well, that would be where theta was minus pi halves or pi halves, so we'll ignore that. That can't be in your domain. And let's see what else we've got here. It looks like what we've got here is first I'm going to pull out the 1/9 out front. I may not properly keep it out there, but for right now let's put it there. Now it looks like to me that's going to be the integral of 1 over sine squared is cosecant squared. Now, I'm not sure this is the way to go, but I think it is. Okay? Now, if you remind yourself what's your antiderivative of cosecant squared, well, I'm pretty sure that's cotangent theta, because the derivative of cotangent is cosecant squared. Right? I believe that's right. So this would be 1/9 the cotangent theta plus c. That's supposed to be a c. Okay. I believe that's what we've got here. Yeah. Minus, I'm sorry, I forgot. The cofunctions are always negative, so that's minus cotangent theta, 1/9 cotangent theta plus c. Now, we're not done though, because you see cotangent, we're here in thetas, whereas we started in x's. So let's see if we can get that to work. Well, here's what we do. Let's draw from this very first line right here. Let's draw our little triangle. Okay, it's going to be a angle here, a 90-degree here. This is your angle theta here. That's my favorite variable for an angle, theta. Okay, now here's your substitution. X equals 3 times the sine of theta. Well, what I'm going to do is divide everything on both sides by 3. Okay, this is a little messy. That says sine of theta is x over 3. Well, sine of theta is the opposite over the hypotenuse, x over 3. Okay, now we have cotangent theta. This is minus 1/9. What is cotangent theta? Cotangent theta is adjacent over opposite, right? So let's do that. Well, what is the adjacent side? We don't know that, or do we? The adjacent side down here is the square root of this squared, 9 minus x squared, because of Pythagorean theorem. This squared plus that squared equal that squared. Okay, so this thing squared would be 9 minus x squared plus x squared. That would be 9. Square root of 9 is 3. Perfect. Okay, so this will be a minus 1/9 times, and what do we say the cotangent was? Adjacent over opposite. So that would be the square root of 9 minus x squared over x plus c. Okay, and that's what their final answer is. Minus 1, well, they wrote it on the line above here, minus 1/9 the square root of 9 minus x squared over x plus c, and then for some unbelievable reason, which is fine, it's perfectly fine, they then took the minus 1 over 9x and then put this as 9 minus x squared plus c. Yep, that's how they wrote it. Okay, which is perfectly fine too. There was nothing wrong with the previous answer, but to get it in terms of x, they put both of those. Okay, these little triangles will come in very, very handy when you're trying to get back from your theta substitution to your x, and that's very, very handy to have that. All right. They then have a technology line at the bottom saying how to do the computer algebra system. I don't own one, but if you have one, you can certainly play with it. Okay? Any questions on example 1? What I'm going to do then is erase what I have, and we'll see how they proceed. Okay? First, note that the basic integration rules do not apply. What they mean by that is you don't have this as a standard integration property, you might say. There's just not one that would fit that. So what do? We looked for the trig substitution. This is a form of that, okay, where a is 3 and x is u, okay, u is x, okay. So with that substitution in mind, you use x equal a sine theta, which in this case is 3 times the sine of theta. Okay, now once you have that, then you can do your x squared, 9 minus x squared, the square root of 9 minus x squared, you already had the x squared, and you do your dx. So do all those calculations, okay? So they start with the dx here, which is 3 times cosine theta d theta. They also did the, they did the x squared here, which is 9 sine squared theta. Then they did 9 minus x squared, which is 9 minus 9 sine squared theta, which is, then take a square root of that, and that gives you a 3 times the 1 minus cosine sine squared theta, which is 3 times cosine theta, and that's where you get this one. Now, once you get all those pieces in place, then we can begin to do our integration. However, they went on and drew the angle that they know they're going to need at the end, the triangle they'll need at the end. And our substitution was, let x equal sine 3 times the sine of theta. So with that in mind, here is your theta. Your sine of theta would be x over 3. That would be opposite side over hypotenuse. And then you have to calculate what this side would be. That would be 3 squared minus x squared, the square root of that. So now we have this. This comes out being exactly this, okay? And it usually will work out that neatly, okay? So once you have all the pieces in place, then you can go back and do your substitution. Here was your original integral, and your dx was the 3 cosine theta d theta, so that goes up top. Your x squared from here is this one, 9 sine squared theta, that goes here. Your square root of 9 minus x squared, that was 3 cosine theta. There that is. This 3 cosine theta, that 3 cosine theta divides away to be 1, and that leaves you the 1/9, pulling this on the outside, the antiderivative of d theta from here over sine squared theta. Well, that is 1/9 cosecant theta d theta, and that happens to be the perfect derivative of minus cotangent theta. So the minus 1/9 cotangent theta. Now, from that, we can go to the, they call that the cosecant rule. That would be fine, whatever. What is cotangent theta? Cotangent theta is adjacent side over opposite side. So it's 9, the square root of 9 minus x squared over x. And that's what they plug in here. Minus 1/9 times the square root of 9 minus x squared over x plus c. And then they group the things together slightly differently and put the 9 in the x in the denominator, minus sign out front, and square root of 9 minus x squared in the numerator plus c. And there you have it. All right. Any question? Note that the triangle in figure 8.6 can be used to convert the thetas back to your x's. Okay? Now, I usually wait till the end to do that. They did it right at the very beginning. It really doesn't matter when you do it. Just don't forget to do it. Excuse me just a minute. I'm still pretty anemic, but I'm also exhausted. So hold on just a minute and let me get a little bit more of some sugar and caffeine. I don't know for sure if that's going to tide me over, but it feels like it might help a little bit. Okay, any questions on example 1? All right. Oh, this is continuing that the cotangent is square root of 9 minus x squared, the adjacent side over the opposite side, which is x. All right. Now, that was example 1. They're skipping example 2, 3, 4 before they get to special integration formulas. So let's us go to the whiteboard and do example 2. Any questions on this before? Let me go back up one before I go. Okay, I'm trying to get the whiteboard to come up. There we go. Now, Okay. Now let me move some things around here. Why they choose to put their taskbar in the middle of the whiteboard, not in the middle per se, but it's just in my way. And why don't they put it off to the side where it's not in anybody's way and you can see more white space? Okay. That's about the best I can do. All right, here's example 2. Find this integral. The integral of dx over the square root of, for some reason I'm on a brown screen. I think I'd rather be on a black screen. Okay, black pen. 4x squared plus 1. Okay. Now, this is not the same form that we had before. Form that we had before was a square root of a squared minus u squared, basically. That is conducive to a sign substitution. This is a plus sign in there. And when I see that inside the radical, I think tangent, because tangent squared theta is 1 plus secant squared theta, right? So it looks like what our substitution should be would be the let, okay, you have to do sort of some backward thinking here. X equal to two times the tangent of theta. Okay, I believe that's our substitution. Let's check it and see if that is going to work for us. Okay, then x squared, for some reason the pen is not writing well, x squared is equal to 4 times tangent squared theta. Okay, and then add 1 to that. I may have done this backwards. Hold on just a minute. I think what I want to do, let 2x be, okay. I've got to get my eraser to come up. There we go. Let 2x equal tangent theta. Okay. I believe that'll work. My brain isn't completely here. It's still trying to sleep off the... I can't get the eraser to disappear now. That's unusual. Sometimes I can't get the eraser to come up, and now I can't get the eraser to disappear. There we go. I'm hit the wrong button, no wonder. Okay, let 2x equal tangent theta, then I hope this is right. If you square that, that would be 4x squared. Okay, when you square 2x, you get 4x squared is equal to tangent squared theta. So I don't need that one. I'm going to try to make this look a little better. Okay. Everything is erasing now. All right. So I don't know what. This is so bizarre. Okay. I can't tell what that is there for. Okay. All right. Let 2x equal tan theta. Then if you square 2x, you get 4x squared. Okay. is equal to tangent squared theta. Then what we're going to do is add a 1 here and add a 1 here. And what does that give you? Now that is an x2 plus 1. It's x squared, 4x squared plus 1. So this would be tangent squared theta plus 1. That would be, then you take a square root of that and the square root of this. Okay, well this would be exactly what you've got here, square root of 4x squared plus 1. That's not part of the 4x squared or the squared thing. This is the square root of secant squared theta, right? That tangent squared theta plus 1 is secant squared theta. Take the square root of secant squared theta and you get secant theta. Alright, that's going in this direction. Let's go down here then and do our other then here. And this would be 2 dx. If 2x is equal to that, 2 dx would be derivative of tangent is secant squared theta d theta. Okay, we don't have a 2 dx, we have just a dx here, so we're going to divide everything by 2 here. Okay, now your dx is secant squared theta. So let's see what our integral is now. The dx is now, I'm going to pull the 1/2 out here. That's that 2 there. Secant squared theta d theta, that's from here, the 1/2 being up front, over, and what was your square root of 4x squared plus 1? That was secant theta, right? So now we have a secant theta down here. Well, this secant theta divides into that one and leaves you a secant theta. Now, you have the 1/2 out here. What is the antiderivative of secant theta? This is one of our, what they call sort of standard integrals. And I'm going to try to flip back quickly. Actually, the easiest place to go was the very front inside cover of your text. Okay, that front inside cardstock material there. Okay, for some reason my pages been up out of shape and it's about to fall off my little desk here. Okay, if you see the integral that says number 12 front inside cover, the integral of secant u du is the log, if I can get my pen in the right place, okay, there we go, the log, natural log of absolute value secant u plus tangent u. Well, let's just call it theta. We don't have to call it u, plus tangent theta plus c. Now, you don't have to include the plus c anywhere else. Okay? Now I can't get stinking book to line up right. Okay. Okay. Now, really important in this case for us to draw our little triangle. So let's draw the little triangle here. It's important in every case. Try to get a horizontal line and a vertical line and let this be your theta. You don't have to know what the theta is, but let's just assume that's your theta there. Okay? Now, our substitution is tangent theta is equal to 2x. Well, let's make that 2x over 1. Well, what is your tangent theta, it's opposite over adjacent. So that's your 2x over here. Adjacent down here, what would make that your hypotenuse? The square root of 4x squared plus 1. Okay, that's exactly what you've got down here. Okay, so let's plug in what we know. That would be 1/2 the log of the absolute value. We can probably lose these in just a minute. Okay, secant theta is hypotenuse over adjacent. So that would be the square root of 4x squared plus 1, which now we see probably why we can lose that, plus tangent theta. Well, tangent theta is opposite over adjacent. That's your tangent, plus 2x. So now you might say, nah, we probably can't lose the absolute value bars, and then we have a plus c. So there's our answer. I don't think there's much more we can do to simplify that. If that were only this term here, yuck. This is totally bizarre. It's just drawing lines wherever it wants to. And now there's the eraser. That line's unnecessary, and this line is unnecessary. Man, that was bizarre. Okay. This part here is always positive, because no matter what value x is, x squared is not negative, times 4, that would be not negative, plus 1, definitely not negative. So this part, okay, is not negative. However, your x here could be negative, and if that's big enough, then that could make that whole thing. So you have to keep the absolute value bar, I think. Let's see what they do. 1/2 the natural log of, they keep the absolute value bars, the square root of x squared, 4x squared plus 1 plus 2x, close the absolute value, plus c. Got it. They didn't put the, I'll do the same thing they did. It's not necessary to have this bracket there anymore, because it's 1/2 the logarithm, then that's the argument of the logarithm plus c. So it really doesn't matter where that you have that bracket in front. I put it there just because showing that's your the result of your integral, okay, is what's inside the bracket. But it's just one term, so you can lose it. All right, any questions on example 2? Okay, now let's move to example 3. All right, to clear this, anyone need it a little bit longer? Okay, so let's go to example 3. Excuse me, I need some water. Okay. Now this example 3, it's not on the PowerPoint, but it is available at larsoncalculus.com. You can see an interactive version of this type of example. Here is your integral. The integral of dx over x squared plus 1. This is raised to the 3/2 power. Now, I'm a little surprised they do one fairly similar to what we just did. Not exactly the same, but very similar. The substitution is very much the same. You have a form. If this had an x up here with the dx, a u substitution does perfectly fine. We don't have an x up here. So now we need to do a trig substitution. And this is again of the form I think of this as thinking of this being a tangent squared plus 1, which is a secant squared. So that's going to be my substitution. Let x equal tangent theta. This is a pretty direct substitution here too. Now again, I like to go in two directions here. Let's first square the x. That gives you x squared is equal to tangent squared theta. Okay, then I'm going to add 1 to that. Make this a plus 1 up here and a plus 1 here. And that gives you your x squared plus 1 is equal to tangent squared theta plus 1. This is exactly what you got here. This is exactly secant squared theta. But you're raising this to the 3/2 power. So you're raising this to the 3/2 power. Well, that would then be x squared plus 1 to the 3/2 power is equal to, now the square root of secant squared would be secant, and now that's the secant cubed. Okay, so now we've got what your denominator is, secant cubed. Let's go back to our other then and do our dx, and if x is tangent theta, dx is secant squared theta, right? D theta, because that's what derivative of tangent is. So let's put it all together. Your integral is now b, your dx is secant squared theta, d theta, that's your numerator part, dx. Your denominator down here is your x squared plus 1 to the 3/2 power, which we found to be secant cubed theta. Okay, well, this secant squared wipes out all but a secant theta down here, and this is simply 1 over secant is cosine. And I hope we all know and love the fact that antiderivative of cosine is sine. Okay, now indirect or indefinite integral. So let's go to our little, goodness gracious, our little triangle here. Goodness, that's an ugly triangle, isn't it? Let this be your theta, and we have a tangent theta is x over 1. Tangent theta is opposite over adjacent. Now that's a 1 there. Okay, not having to do with that. Okay, now we're looking for sine theta, and sine theta would be opposite over hypotenuse. What's your hypotenuse? The square root of x squared, if the pen would show back up, x squared plus 1, which is exactly what you've got here. So this is, not that that matters any, this would be sine theta would be the square root of, I'm sorry, goodness, I'm hanging, just barely hanging in there. Well, I can't get my pen back. Okay. The sine of theta is opposite over hypotenuse. So this would be x over the square root of x squared plus 1 plus c. Probably should have written the plus c in here too. Okay, now that's what we got. The x over the square root of x squared plus 1 plus c. Yes. that's what example 3 gave us as well. All right. Sorry, folks. I'm going to have to stop for a little more caffeine. I'll be right back with you, but boy, I am running ragged. So hold on just a minute. Partly as we left so early, we didn't really have breakfast. We sort of snacked on the way, so part of what I'm going through now is probably absolute hunger too. All right. Now, the first 3 examples we've done were all indefinite integrals. Okay, what if we have definite integrals? Let's see if there are any major differences there. Not really too much. Anyone need this left a little longer? Can I clear it? Okay. Here's example 4 on page 544. Okay. Here's our integral, if I can get my pen to show up here. There we go. The integral from the square root of 3 to 2, and our integrand is going to be the square root of x squared minus 3, and our denominator is going to be an x, and then we'll have our dx. Okay, now if you recall what our 3 forms are, one form is a squared minus u squared. That's a sign substitution, because sine is 1 minus sine squared is cosine squared. So that's the form we'd normally have there. This is reverse of that. The tangent substitution was a form that was going to be like x squared plus a squared, because tangent squared plus 1 is secant squared. Well, that's not what we've got either. What we have is x squared minus 3, which is going to be of the form kinda, secant, because x is going to be a secant substitution, and the reason is because secant squared minus 1 is tangent squared. So that's where we're going from. Now, what we've got is a little bit of manipulation here to do. Let's let our x equal, we know we're going to have a secant, okay, theta. Okay, now if you recall, this thing right here has to be an a squared. Well, that's a 3. Okay, so basically that means a is the square root of 3. Okay, so there is your substitution. All right, now let's carry that out here and first square it. That would give you x squared would equal 3 times secant squared theta. Okay, if this is your substitution, when you square the root 3, you get 3. Square secant, you get secant squared. Okay, now next thing we're going to do is subtract 3 from that. So subtract the 3 here and subtract the 3 there. Okay, and what that gave you is, well, and then let's go on and take the square root of this and the square root of that. Okay, so this is your I wrote down the 1 here. That should be a 3 here and a 3 there. Don't know where that came from, but anyway, subtract 3 from both sides of that. Okay, and that gives you your numerator here is equal to this. Okay, well, what is that? That would be the square root of 3, if you factored that out, times square root of the square root of secant squared minus 1. Well, that is tangent squared. Square root of tangent squared is tangent. Okay. Now we've carried that about as far as we can. Let's go back here and do our then on this side. Dx is equal to, now if you remember what the derivative of tangent, well, let's just write down our root 3, okay? And derivative of tangent is, derivative of secant is secant theta tangent theta. You can go back to the front inside cover and look at it. Secant theta tangent theta d theta. Okay, I'm losing it again, folks. I'm so sorry. If you go back to that front inside cover, that cardstock page there, the very, very beginning of your text there, okay, and you, goodness gracious, see the basic differentiation rule there, derivative of, it's number, there we go, number 17 on that, d by dx of secant u, which is what we've got here, is secant u tangent u du. So we got secant theta tangent theta d theta, with the square root of 3 out front. All right, so let's adjust this, if I can get my pen to show up. Now let's leave the integral off for right now, okay, the limits here, okay. Let's see what we've got here. Your x, the square root of x squared minus 3, that was the square root of x squared minus 3, and we found that to be the square root of 3 times tangent theta, okay. Now your d theta, which is also up here, is going to be, dx here, is going to be the square root of 3 times secant theta tangent theta d theta. Okay, so your first part here is that thing. Your second part here is that thing. And then you're dividing this by x. Well, x is the square root of 3 times the secant theta. That's what your x was. All right, so let's get rid of some things here. One of these square roots will divide out one of that square root down there. This secant theta here will divide out the secant theta there. And what does that leave you with? Now, again, ignoring my limits for now. Don't know if that's fair to do yet or not, but I think it's okay. That'll be the integral. I'm still treating this like a, so what we have left is the square root of 3. So I'm going to put that out front here, from here. And then you have tangent squared theta d theta. Okay. Now, don't get carried away here and get these confused. Sorry, I'm losing it again. The antiderivative of tangent squared is not secant squared, secant theta. You got them backwards. The derivative of tangent is secant squared, not that the derivative of secant is tangent squared. So we have a form here that has a tangent squared in it. So now we're going to have to go to one of our trigonometric integrals to figure that one out. Okay? Now, what we can do here is this. It's not too far removed. This is going to equal to the square root of 3. Okay, but just like what I said from back that we did earlier, tangent squared is secant squared minus 1. So this is going to be secant squared theta minus 1. what I'm going to do is make that secant squared theta d theta times or minus the integral of d theta, 1 times d theta. Okay. Now again, we're dealing indefinite integral. We're going to come back and fiddle with the other part next. That's the square root of 3. Now, the reason we did this, what's the antiderivative of secant squared? That's the one that we do know. That's tangent squared theta. Tangent theta, not tangent squared. Minus theta. Okay, the antiderivative of d theta is theta. Okay, now, now I've avoided as much as I can. Let's go back and do our little triangle. That's going to be helpful for a little bit here. If I can find my pen again. There it is. Okay. So let's do from this substitution here, secant theta is x over square root of 3. So let's do our little triangle here. This is your theta. Secant theta is hypotenuse over adjacent. So that puts the hypotenuse here, x, over the square root of 3 here. That's the adjacent. And that leaves this side over here being the square root of x squared minus 3. Okay, which is exactly what we have there. Okay, now, if that's your theta, this is your opposite and that's your adjacent, then the tangent is opposite over adjacent. So this part here would be the square root of 3 times the opposite side over the adjacent side. That's what your tangent theta is. So that's the square root of x squared minus 3. This is so aggravating. X squared minus 3 over root 3, opposite over adjacent. I'm losing my voice. Okay. And then, now this is the part that's a little bizarre. Go back here and say that what we were saying before, x over root 3 is the secant of theta. So the inverse secant of theta, I didn't put my equal sign in there. I said it but didn't write it. Okay. X over root 3 is equal to secant theta. So what I would like to do with that is to rewrite this as the square root of 3 over x is equal to cosine theta because of reciprocal identity. Okay, so that makes the inverse cosine theta is equal to the inverse cosine, aggravating, inverse cosine of root 3 over x. Alright, so then this would be the inverse cosine of root 3 over x. Okay, now the only thing I can see to make this look a little bit better is on this first term here, let the root 3's go out, and this gives you the square root of x squared minus 3, no, just that, minus the inverse cosine, or root 3 times the inverse cosine of the square root of 3 over x. Now, but this is where we plug in our limits here, 2 and root 3. And you see we're still in x's here, so that's going to be fine. So what we have here, if we plug in 2 for x squared, that would be 2 squared is 4. The square root of 4 minus 1, that's just 1. Okay? Minus, now, when you plug in a 2 for your x here, you have the inverse cosine of square root of 3 over 2. Well, what is the inverse cosine of square root of 3 over 2? That is 1/2. I'm sorry, pi halves. No, not pi half. Pi 6, I'm sorry. I'm saying everything backwards now. That's pi 6, so that would be root 3. I don't know why that's showing up there. Root 3 times pi 6. Pi over 6. Okay, that's the first part there. Minus, when you plug in a root 3 here, this would be minus, well, the square root of 3 squared is 3. 3 minus 3 is 0, so that's going to go away. And then you have minus a minus, and now you have the inverse cosine of root 3 over root 3. Well, root 3 over root 3 is 1. Inverse cosine of 1 is 0. So I think that's your answer right there. 1 minus root 3 pi over 6, which if you wanted to, you could fiddle that around a little bit, but I think that's what they give us. Now, they come up with it reversed. Well, it may be because I misrepresented the problem to begin with. No. Oh, I'm sorry. I'm looking at the wrong page. Yeah. 1 minus root 3 pi over 6. Got it. And that's what they got. They pulled out their handy-dandy calculator, which mine is not charging, so I hope it will has enough juice to do it. All right. Goodness, I am so tired. 1 minus I'm going to have to turn my thing sideways. There we go. 3 square root times pi divided by 6 equal. And they got about 0.0931, and that's what I got to. 0.0931, blah, 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 blah. Okay. Now, got to get my charger back up here. And they then show how you can go back and do your actually, the way they work their problem, they changed the limits to your thetas, which worked fine. Okay, I went back to the x's because I thought that would probably work out just as well, which it did. In fact, it looked like it took fewer lines for them to do it the way I did it than the way they did it. So both of those answers are correct. Okay. Now, they do mention some other things here, for instance, making sure that your limits of integration make sense. They did another example, but put the negative root 3 on top and the negative 2 on the bottom, and that gave us the opposite answer as what we just did. Okay? And then they show some other completing the square type forms that you could do just as well. Usually those are a lot more involved. So I think where we are now is to go back to the PowerPoint. Anyone have questions on this one before we leave? I know Brandon earlier said he didn't have a microphone, so I hope you have no questions, but if you do, please let me know. And if some of the rest of you, if he shares a chat that I don't see, let me know. Okay, so let's go back to the PowerPoint, which I think is right here. Okay, this is the bottom of page 545. Trigonometric substitution can be used to find the three integrals listed in this theorem. I think we've seen these before, something pretty close to it. These integrals will be encountered several times, so here's what they are. If you have the square root of a squared minus u squared, okay, that you don't have a u somewhere else that you can fiddle with, this is going to be a sign substitution, okay, because it's going to be, the substitution is going to be excuse me, I am so tired. Let me get a little more caffeine here. I don't know how I'm going to make it through 3 classes, much less one. Of course, eating a little bit of lunch in a short time probably is going to be helpful. Let's see. Okay. This will be a sign substitution. Let u equal a times the sine of theta. Okay, and that will give you, and then you'll have an inverse sign show up there. Okay, so expect that. This one is your secant substitution. Let u equal a times the secant of theta. Okay, and you won't see a secant show up here, but you will see a log, and you'll see where that comes from. And then this one is let u equal a times the tangent of theta, and that will work out there too. And you won't get an arctangent either. You'll get a u substitution. I mean a log form. So stand by for those. All right, let's move on to applications, which the last thing we do in this section. There's 2 examples here, so let's do at least the first one here. Find the arc length of the graph of f of x is equal to 1/2 x squared from x equals 0 to x equals 1. Okay, there's the figure for it. Thank you very much for drawing that for me. Okay, and that's from the curve 0, 0 when x is equal to 0. That would be 0 when x is equal to 1. That would be 1/2. Okay, so that's the arc length we're looking for. Now, a little bit of refresher on how in the world we do an arc length. Okay, well, if you recall from doing an arc length, one of the things you're going to do is do an f prime. So if this is your f prime would be x. 2 times 1/2 is 1 times x. Okay, so there's that part. Next thing you do, you square it. So f prime of x squared would be x squared. Okay, that's pretty straightforward. Okay, next thing you do 1 plus this, so that you have 1 plus x squared. Okay, and then you take a derivative of it. I mean, you take the square root of it. Okay, and that gives you your integral dx. Okay, so that's the arc length S is equal to that expression there. Well, that's a good old tangent substitution. Let x equal tangent theta. Then we'll go this way first. X squared is equal to tangent squared theta. X squared plus 1 is tangent squared theta plus 1. And then you take a square root of this, and you get a square root of that, and that would give you that being equal to tangent squared theta plus 1 is secant squared, so you take the square root of secant squared and you get secant theta. Okay, so that's what this thing is here, is your secant theta. That's going to go in. So let's go down here for the next then and do your dx. Derivative of tangent is secant squared theta d theta. Derivative of tangent is secant squared theta d theta. So let's go back to our integral. S is equal to, oh my goodness gracious, the integral from your x's are going from 0 to 1 of your this thing here, square root of 1 plus x squared, that is secant theta. Okay, sorry about this. Your x's are 0 to 1. So let's hold off for these for just a moment here. Goodness gracious, I'm so tired. Okay, we'll hold off the limits for right now. We'll put them in just a few minutes. Okay, this square root of 1 plus x squared, or x squared plus 1, is secant theta. Okay, and your dx is secant squared theta, so that brings it up secant cubed theta d theta. Okay, now I don't know which way I want to go on this, whether I want to go on and integrate this and then plug back in. Let's go on and deal with the limits. Okay, if x is equal to tan theta, when x is equal to 0, theta is equal to 0. Okay, and when x is equal to 1, from right here, I didn't put them in, I should have 0 to 1, sorry, because that's where your x's are. Theta is equal to, right here, pi fourths. Alright, now what in the world is the integral of secant cubed theta? Again, this is a good handy dandy one to go back to your integration table, front inside cover of your text, and secant cubed oh man, they don't show it here. The back part of your book, they have a fuller table there. And this is in the appendix back here. That's in front of the index, and I believe in front of your answers to the odd number problems. Oh, here it is. I have it marked. Okay. And this is forms involving secant u. This is page A5 at the back of your book, and we're looking for secant cubed. And I don't think they have secant cubed, but they do have secant to the n. Okay, and this is number 69 back here at the back. Okay, and I'm going to try to write this down here. I may not have room, so I may have to do it somewhere else. This will be secant to the n minus 2. Now n here is 3, so n minus 2 is 1. So this will be secant theta, sorry, times tangent, and that will also be theta, yeah, over n minus 1, that would be 2, okay, plus n minus 2, which would be 1, over n minus 1, which would be 2, times the integral of secant to the n minus 2, which would be secant theta, okay, d theta. Now, all right, and then that last integral, secant theta, is the one we done a couple of times earlier, the log of secant u plus tangent u, absolute value. So let me get my book closed up again, and let me come over here and write down that answer. Okay, so the arc length is it's beginning with right here, secant of pi fourths. Okay, now got to remember what secant of pi fourths is. Cosine of pi fourths is square root of 2 over 2. So secant of pi fourths is square root of 2. Okay, so this will be, if I can find, there it is. Okay. Oh goodness, my stomach is hurting like crazy. Probably hunger. That's square root of 2 times tangent of pi fourths is 1 over 2, so that's the first part of that one, plus 1/2, and remember what the integral of secant is? That is the natural log of absolute value secant theta, yeah, secant theta plus tangent theta. Okay, and we'll evaluate that from 0 to pi fourths. Now what I haven't done yet, and I realize this, I didn't substitute in here the zeros, but we'll get there in just a second. So this is the square root of 2 over 2 plus, and here we have secant of theta, let me put my 1/2 there, the log of secant of pi fourths is root 2 plus 1, goodness gracious, my stomach is hurting, okay, minus, now let's do secant of 0 is 1, tangent of 0 is 0 over 2, so that's going to be a 0, and then this one, when you do up here, then you put a 0 in here, that's the 1/2 the log of secant of 0 is 1, and plus tangent of 0 is 0, so the log of 1 is 0. So that contributes nothing. Okay, I know that was a lot of blah blah blah. So here is your answer. Okay, I don't know how they write it. I think I would write it as root 2 plus the log of root 2 plus 1 all over 2. All right, now 1/2, okay, they did root 2 plus log of root 2 plus 1. Okay, let's see if they did their calculations right. Oh man, we've just gone over, haven't we? Sorry about that. Let me get my calculator up. Okay, and cleared. Okay, there we go. Let's do the root 2 first. 2 square root. Okay, got that. Plus the log. Okay, I have to do my argument first. So I have to do an open parentheses. I hope it opened. Root 2 plus 1, close parentheses, do a natural log, equal, and then take half of it, divided by 2. And I got 1.148. Yep, that's what they got. Okay, so that was it. Sorry, took a bit long on the calculation there. We didn't do example 6, but if I remember correctly, on example 6, they go through all sorts of rigmarole and then say, by the way, you really can't do the integral. So I saw no reason to do any more. So we'll just exempt example 6. If you want to do it, okay? But they wind up saying, well, to find this, you have to do this, and then the details of integration are left you to complete. Intuitively, you would say the fourth blah, 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 and it's all estimated. So we're not going to take class time to do that. All right, so let's, homework exercises on 8.4, either 3 or 5. Oh, by the way, the concept check, not a bad idea. Do the concept check. That's 1 and 2. Or at least 1 if that's all they got in the, at calcchat.com. Then do either 3 or 5, both at CalcChat, 7 or 9, both at CalcChat, 7's at CalcView, 11 or 13 are at CalcChat, 15 or 17 are at CalcChat, 19 through 20 or 31 are at CalcChat, 19's at CalcView, 33 or 35's at CalcChat, 35's at CalcView, 37 to 41 are at CalcChat, 37's at CalcView, 43's at CalcChat, 45 should be at CalcChat. There's true false, either 47 or 49 should both be at CalcChat. Then 51 should be at CalcChat, 53 should be at CalcChat, 55 should be at CalcChat, 57 should be at CalcChat, and then if you want to, try the 59 again. That's similar to that last example we did. This one should work a little bit better. So I'll say do any of the odds 59 through 67. I'll let you choose if and when you want to do any of those. That should be at CalcChat. Okay, we'll begin next time in section 8.5, partial fractions. And I'll try to remember when 4 o'clock gets here, if I'm not passed out completely, to try to get your PDF version of the second test out there for you. Okay? Any other questions? Oh, let me just quickly go through this. Okay? Here's what they do. Refer to the arc-length formula, and remember that's what we did. You take a derivative of your function, square it, add 1 to it, take a square root of that. This is going from 0 to 1. that gives you this substitution, which is a tangent substitution. And they skipped lots and lots of steps there and came up with secant cubed theta d theta. And then they jumped right to the formula that we went to the back of the book to get, and wrote that down, and they came up with that answer, which then they calculated to be about 1.148. And that is the end of uh, 8.4. We will move on to 8.5 next time. Any last thoughts, parting shot? Sorry, we ran over 10 minutes. Sorry about that. Okay? All right, we will see you then on Wednesday. Please remember, if you're eligible to vote, please vote. Okay? If you haven't already, please get by there and vote. Good deal. Thanks much. Take care. See you Wednesday. Bye-bye.